Welcome to Sheridan College's Introduction to Instrumentation. This lesson is a part of Module 3, Temperature Instrumentation, and shall focus on mechanical thermometers. After completing this lesson, you'll be able to identify manual thermometers and explain how a bourdon tube is used to measure temperature. We are all familiar with thermometers. They are a mechanical or electrical scale device that measures temperature. In our last lesson, we discussed thermal expansion. A thermometer uses this principle. The volumetric expansion or thermal expansion of liquid is typically many times greater than that of glass, which tends to be very stable. Since the volume of liquids changes more than the volume of glass, the liquid is forced up or down a tube and changes the temperature. The liquid and glass thermometer was invented by Daniel Fahrenheit in 1714. It took him 10 years to perfect his temperature scale. His version was filled with mercury, but most modern units are now alcohol-based. Many industrial-grade mercury-filled thermometers are still in use. They are very reliable and resilient. That being said, be aware that should one break, find out what the material that was contained in the thermometer was and take appropriate cleanup actions. Mercury thermometers have a range of -37 to 356 degrees Celsius, or -35 to 673 degrees Fahrenheit. However, nitrogen-filled models can measure up to 800 degrees Celsius since the nitrogen raises the mercury's boiling point. There are many available and many mounting configurations. Notice that neither model are suitable for temperatures below -37 since the mercury will freeze solid. Most modern liquid and glass thermometers are alcohol-based, although some use a gallium, indium, and tin alloy. A special liquid and glass thermometer is the maximum temperature thermometer. Just above the mercury's bulb, the tube narrows. As the temperature rises, the mercury is squeezed up, but the tube traps the mercury at the highest temperature when the temperature cools. In an industrial environment, the glass tube needs mechanical protection. A metal display plate provides protection and has the scale engraved or printed on the side. The mercury or alcohol is stored in a metallic bulb or probe that can be mechanically inserted into the process to be measured. Unfortunately, there are some limitations to a liquid and glass thermometer. First of all, they're not normally automated, so they act as a visual reference or guide. And the other thing is the glass can become thermally unstable at higher temperatures, so the upper end is limited. The next type of thermometers we will be discussing use bimetallic thermal expansion to measure temperature. When discussing bimetallic, we are not referring to an alloy. An alloy is a mixture of two or more metals. Brass, for example, is an alloy of copper and tin. But as an alloy, the metal reacts homogeneously to the combined metals. When two metal alloys with different thermal expansion coefficients are fused together into a single strip, the strip reacts to the temperature changes. As the heat is applied, the bimetallic strip will deflect in one direction and will return when the temperature lowers. Bimetallic elements are used as control elements. When a bimetallic strip is combined with an adjustable set point, the deflection caused by the temperature changes can be used to control heat, such as a thermostat. In the picture, you'll notice that the brass cylinder on the top actually is where the dial goes. As you rotate that, it will lower a screw, which will close the gap between the set point and the bimetallic strip. When you turn it the other way, it opens the gap, requiring more heat to satisfy the bimetallic strips. You may recall from our pressure modules that bimetallic strips can also be formed into spirals or helixes, which expand torsionally and therefore can be used to move a mechanically linked indicator arm. The helixes or spirals are very sensitive to changes in heat and are usually very small and fragile. The spiral shown here not only expands with heat, it also rotates. You can imagine connecting an indicating arm to the outer arm of this spiral. Here we have the very common meat thermometer. At its core, it uses a bimetallic helix to move the temperature needle. Bimetallic thermometers have a normal operating range of negative 300 to 800 degrees Fahrenheit. Of course, your dinner would probably be ruined at that temperature. We are now going to discuss using pressure to measure temperature. In Module 2, we discussed a Bourdon tube. Recall that a Bourdon tube was a bimetallic tube, often shaped into a C. And then no matter what was in the tube, liquids or gas, the tube deflected with changes of pressure. We now also know that bimetallic metals also respond to changes in heat. Therefore, it is a simple matter to repurpose the Bourdon tube to measure temperature, since temperature and pressure are interlinked. Recall that when the pressure goes up, the temperature rises, and when the pressure drops, the temperature falls. It is equally true that when the temperature goes up, the pressure will increase, and when the temperature goes down, the pressure drops as well. Bourdon tube thermometers can be either filled with a liquid or filled with a vapor. When filled with a liquid, a capillary tube is filled with the fluid and is connected to the Bourdon C tube with an umbilical tube. As the capillary is exposed to temperature, it forces the fluid up and deflects the tube. The capillary tube is inserted into the process, and as fluid expands or contracts with changes in temperature. While the C shape is quite common, they're also available in spiral or helix formats. The gauge shown is a water temperature, and is used to determine the temperature of an engine block. The capillary is inserted into a water jacket, and the Bourdon tube is behind the glass of the gauge. The other type of Bourdon tube thermometer is the vapor pressure spring thermometer. When water or liquid is boiled, it produces steam, a vapor. As discussed in the last lesson, vapor has tremendous amounts of force. A vapor pressure thermometer uses the expansive force of a vapor to create a pressure that can be then measured either with a Bourdon tube or a capillary tube. As the liquid-filled bulb or capillary tube is exposed to heat, the liquid inside begins to boil, creating a vapor. The higher the heat, the more vapor is created. These kinds of thermometers can measure very high heats until the liquid reaches its critical point, which is the maximum temperature it can measure. The critical temperature is the point where no more pressure or heat will change the vapor into a liquid. At this point, the device will not generate any more readings since the entire volume of the liquid is suspended as a saturated vapor. Just like the liquid-filled Bourdon tube, vapor pressure springs are also connected to a Bourdon tube. The only difference is the medium of deflection for the tube itself. Unfortunately, vapor expansion is not linear. They can be very, very accurate, but you must select the correct unit within their linearity range. Now let's think a little bit about hydrostatic influence. When we did Module 2 and we looked at pressure, the location of a pressure gauge was dependent upon hydrostatic pressure. If it was raised up or raised down relative to the hydrostatic pressure being measured, it would influence the pressure gauge. Thermometers are no different. If the thermometer is placed higher than the spring indicator mechanism, the hydrostatic pressure will develop and errors will occur. Because vapor-filled units are not filled under pressure or vacuum, they too have the same hydrostatic generated errors if the height is not accounted for. We have examined some common forms of mechanical or manual thermometers, such as the liquid and glass and variations of the Bourdon tube. Because of the proven reliability and relative low cost of these thermometers, we will likely continue to use them for many years to come. Thank you for watching.